my dear friends, welcome to my YouTube channel. This is Professor Dattu Patel, Assistant Professor from LJ Institute of Engineering and Technology. Earlier lecture, we already discussed about sequence, convergence and divergence of the sequence and few examples of that. Today's session, we are going to discuss about monotonic sequence, bounded sequence and sandwich theorem. Let's see firstly monotonic sequence. If our sequence is either increasing or decreasing, then we can say that it is monotonic. Let's see first increasing sequence. If un which is less than un plus 1 for all n greater than equal to 1, that means u1 less than u2 which is less than u3 and so on, then we can say that our sequence is increasing. Let's see one example. Example is n square plus 1. Now substitute this sequence for n equal to 1, then we get 2, n equal to 2, then we get 5, n equal to 3, then we get 9 and so on. Means whenever we put the value of n 1, 2, 3 and so on, then we get our sequence is 1, 5, 9 and so on, which is increasing mode. Now plotting that sequence in this graph, then we show this shape which is indicated by the exponential growing shape. Now let's see the decreasing sequence. If u of n which is greater than u of n plus 1 for all n greater than equal to 1, that means u1 greater than u2 which is greater than u3 and so on, then we can say that our sequence un is called decreasing sequence. Let's see one example of the decreasing sequence which is 1 upon n. Then substitute the values of n equal to 1, then we get 1, n equal to 2, then we get 1 half, n equal to 3, then we get 1 by 3. Means whenever we increase the value of n, then sequences which is decreases like as 1, 1 by 2, 1 by 3, 1 by 4 and so on. In this graphical representation, plotting our sequence 1, 1 by 2, 1 by 3 and so on, then shape of this graph which is exponential decaying shape. Now move to our few examples of the monotonic sequence. First example, prove the sequence 3 by n plus 2 is decreasing. First, whatever the sequence 3 by n plus 1, that is our un. Now replacing n as a n plus 1, that implies u of n plus 1 equal to 3 by n plus 3. Now here denominator portion n plus 2 which is obviously less than n plus 3. Now reciprocal of that terms means that 3 by n plus 2 which is always greater than 3 by n plus 3. That implies we can say that un which is greater than un plus 1 for all n greater than equal to 1. Therefore our sequence is decreasing. Now let's see one more example of the monotonic sequences. Prove that the sequence is n square upon n square plus 1 is increasing. Here it is not necessary to check the monotonic sequence with the help of un greater than un plus 1 or un less than un plus 1. Another method to checking the monotonic sequence is exist or not, then we are going to subtraction of the two consecutive sequences. Means that subtraction of the un plus 1 minus un. If answer which is greater than 0, then we can say that our sequence is monotonic increasing. If answer means subtraction un plus 1 minus un which is less than 0, then we can say that our sequence is decreasing. This is another method to finding the sequence is increasing or decreasing with the help of successive subtraction of two consecutive sequences. Let's see. Here u of n plus 1 equal to n plus 1 whole square upon n plus 1 whole square plus 1. Now with the help of basic algebra formula, we get in numerator portion n square plus 2n plus 1, in denominator portion n square plus 2n plus 2. Now subtraction of the two consecutive sequence which is un plus 1 minus un, then substitute the values of un plus 1 and un. Now cross multiply that particular sequences and simplify that term, means some of the terms are cancel out and we get 2n plus 1 in denominator portion, n square plus 2n plus 2 into n square plus 1, which is greater than 0. Means subtraction which is greater than 0. Then we can say that sequence is increasing, means monotonic increasing sequence. Let's see one more example of the monotonic sequence, which is un equal to n upon n square plus 1 is decreasing or not. Then here un equal to n upon n square plus 1. Now substituting the values of n as n plus 1, then n plus 1 upon n square, n plus 1 whole square plus 1. Now with the help of basic algebra formula, then we get n plus 1 upon n square plus 2n plus 2. Now with the help of two consecutive sequences of subtraction, means un plus 1 minus un. Now substituting the values of un plus 1 and un and cross multiply it and simplify that term, then we get in numerator portion minus n square minus n plus 1 and denominator portion n square plus 2n plus 2 into n square plus 1. Now substituting the values of n belongs to capital N for all the values of n, we get which is less than 0. If our answer which is less than 0 for all n belongs to n, then that means we can say that our sequence is decreasing. Now let's see the next topic, which is bounded sequence. Basically bounded means finite. A sequence un is bounded above if there exists a number capital M such that un less than or equal to m for all n greater than equal to 1. Let's understand with small example. Here sequence is minus n, means u of n equal to minus n. Now in this particular sequence we substitute the values of n equal to 1, n equal to 2, n equal to 3 and so on. Then we get our sequence is minus infinite and so on, minus 3, minus 2, minus 1, etc. Now in this sequence we put the n equal to 1, 2, 3, 4, 5 and so on. Then we get minus 2, minus 1, minus 2, minus 3, minus 4, minus 5 up to minus infinite. Means maximum value of that particular sequence is minus 1. Means our minus 1, that is upper boundary. Means our sequence cannot exist from the minus 1. Means minus 1 indicate by the our capital M. Then our sequence is bounded above by minus 1. Now let's see the bounded below. A sequence un is bounded below if there exists a number small m such that un which is greater than equal to m for all n greater than 1. Let's see the one example for the bounded below. Here sequence un equal to n. Substitute the values of n equal to 1, 2, 3, 4 and so on. Then we get the our sequences 1, 2, 3, 4, 5 so on up to infinite. Then minimum value of that particular sequence is 1. Means remaining all the terms are greater than 1. Means lower boundary minimum value is 1. Means lower boundary, that is 1, and other sequences value which is more than 1. Means we can say that small m which is 1 and un which is greater than equal to m. Then we can say that our sequence which is bounded below by 1, means this sequence indicated by the bounded below. Now next one is a bounded sequence. If it is bounded above and bounded below, then we can say that un is a bounded sequence. Let's see one example of the un. Here un equal to 1 upon n. Now substituting the values of n equal to 1, 2, 3, 4 and so on. Then we get the values 1 by 2, 1 by 3, 1 by 4 and so on. Whenever we put the infinite, then 1 upon infinite, that is 0. Means in this particular sequence which is lies between 1 and 0, means 1, 1 by 2, 1 by 3, 1 by 4 up to 0. Means upper boundary, that is 1, and lower boundary, that is 0. Means our sequence which is lies between 0 and 1, means both the boundaries are fixed. That means we can say that our sequence is a bounded sequence. Let's see the one theorem of the bounded sequence. Means every bounded sequence or monotonic sequence is always convergent. Let's see the few examples of the bounded sequence. First example, prove that sequence un equal to 2n minus 3 upon 3n plus 4 is monotonic or is it convergent. Firstly, un equal to 2n minus 3 upon 3n plus 4. Now substitute the n as n plus 1. Then we get 3n minus 1 upon 3n plus 7. Now we have to check the given sequence is monotonic or not. Means subtraction of the two consecutive sequences, which is un plus 1 minus un. Now substitute the values of un plus 1 and un and cross multiply of 8 and simplified it. Then we get 7 upon 3n plus 4 into 3n plus 7, which is always greater than 0. Therefore our sequence un is monotonic sequence. Now in this sequence, substituting the values of n equal to 1, 2, 3, 4 and so on, then we get which is in lies between minus 1 less than un less than 1. Means whatever the sequence which is lies between inside the bracket minus 1 to 1 for all n greater than equal to 1. Therefore we can say that un is a bounded sequence. So according to the theorem, if un is monotonic increasing sequence and bounded sequence, then it is convergent. Now let's see one more examples of the bounded sequence. So that the sequence un whose n term is un equal to 1 plus 1 by 3 plus 1 by 3 square plus and so plus 1 by n is monotonic increasing or is it convergent. Firstly, here un equal to 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 cube and so on plus 1 by 3 raised to n. Now substitute the n as a n plus 1, then we get n terms of the n plus 1 terms of the sequence, which is 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 cube and up to plus 1 by 3 raised to n plus 1 by 3 raised to n plus 1. Now subtraction of these two consecutive sequences un plus 1 minus un, that implies and we get 1 upon 3 raised to n plus 1, which is greater than 0 for all n belongs to n. Therefore sequence un is monotonic increasing. Now here our sequence un equal to 1 plus 1 by 3 plus 1 by 3 square and so on. Means here this sequence which is indicate form 1 plus r square plus r cube and so on. Means with the help of sum of geometric progression, if r which is less than 1, then we have the formula a inside the bracket 1 minus r raised to n upon 1 minus r, which is already studied in earlier standard. Now substituting the r as a 1 by 3, then we get 1 inside the bracket 1 minus 1 by 3 raised to n upon 1 minus 1 by 3. Now simplify the denominator portion, then we get 3 by 2 inside the bracket 1 minus 1 by 3 raised to n. Now whatever the values of n we put in last equation, then maximum value of this term which is 3 by 2 and remaining values are which is always less than 3 by 2. Means we can say that our sequence is bounded above by 3 by 2. Means our sequence is monotonic increasing and bounded above. Then according to the theorem we can say that it is convergent. Now let's next topic, which is sandwich theorem. Sandwich theorem, which is also called the squeeze theorem. Here consider the three sequences un, vn and wn. Now if un which is less than or equal to vn, which is less than or equal to wn for all n greater than equal to n0, and we find the limit of first sequences and last sequences both are same, means limit n tends to infinite un which is l, also limit n tends to infinite wn which is also l, then by default middle term of sequence which is limit n tends to infinite, Vn is equal to L. Now let's see the one examples of the sandwich theorem. Discuss the convergence of the sequence un equal to sin n by n. You know about sine is a continuous function, means that sine which is lies between -1 to 1, means minimum value is -1 and maximum value is 1. Since -1 less than or equal to sin n less than or equal to 1. Now multiplying this sequence with 1 upon n, that implies -1 upon n less than sin n by n, which is less than or equal to 1 by n. And according to this sandwich theorem, here these are the three sequences: -1 upon n, sin n by n, and 1 upon n. Then we find the limit of first and last sequences, means limit n tends to infinite -1 upon n. Then we apply n as a infinite, then we get 0. Again we apply limit in last sequence, that is 1 upon n. Then limit n tends to infinite 1 upon n, that is also 0. Then according to this sandwich theorem, -1 upon n, limit of -1 upon n is 0 and limit of 1 upon n which is also 0. Then by default limit n tends to infinite sin n by n, which is also 0. Therefore we can say that our sequence un sin n by n is converges to the 0. Let's see one more examples of the sequences of the sandwich theorem. Here sequence un equal to cos square n upon n. As you know about the cos is also continuous function, then cos square, then value of cos square which is lies between 0 and 1, means 0 less than or equal to cos square and less than or equal to 1. Now multiply with this sequence by 1 by n, then we get 0 less than or equal to cos square n by n less than or equal to 1 by n. Now here we have total 3 sequences. Then we find the limit of first sequences and limit of last sequences. Then limit n tends to infinite 0, that is but obvious 0. Now last sequence, then limit n tends to infinite 1 upon n, then n as a infinite, then 1 upon infinite we get 0. Then first and last sequence which is 0. Then according to this sandwich theorem, middle sequence limit n tends to infinite cos square n by n, which is also 0. Then we can say that given sequences cos square n by n is converges to 0. This is all about the topics bounded sequence, monotonic sequence and sandwich theorem. I hope you guys learned something from this video. If you like this video, then thumbs up. If you think that this video will help some of your friends, then do the share with them. If you want to watch more tutorials like this, you can subscribe my YouTube channel. If you subscribe my YouTube channel, then when I upload the video, you get the notification. Thank you so much for watching me.